So let us give some motivation for the definition of Cech cohomology. So in practice, we often run into this beautiful short exact sequence of sheaves. But the sad fact is that these do not lead to a short exact sequence of global sections. A fancy way of saying this is that the global section functor is not right exact. But not all is lost. We want to construct the cohomology theory in such a way that, okay, we might not have a short exact sequence here, but we will have a long exact sequence of cohomology. In particular, today we'll discuss how we will define Cech cohomology so that we can extend this sequence to H1 of K. Okay, to do that, first let us explain why we have this failure. Now, for a map of sheaf, if it's injective, then it's also injective on section. But if it's surjective, it does not necessarily mean it's going to be surjective on sections, and let's see why. So for maps of sheaves, injectivity and surjectivity are both equivalent to injectivity and surjectivity on stock, so I will just write this as this. Now we want to explain why injectivity on stock implies injectivity on section, but surjectivity on stock does not imply surjectivity on sections. Alright, so let's say that this map is injective on stock, right? Now, let's see why it would be injective on section. So let's say F is a section over U of this big F, right? And say F maps to 0, then locally, F must be 0. Because of the injectivity on stock, we know that there must exist a cover UI of U such that F restricted to each of these UI must be 0. But then by sheaf axiom, these F restricted to UI, they glue to F, right? So F is itself must be 0. Alright, so far so good. Let's see what's wrong in the case of surjectivity. Now, similarly, F, suppose the map from the sheaf F to G is surjective. That's equivalent to saying that the map on stock is surjective. Let's see why the map on sections might not be surjective. So, let's say we have a section little g here of G on U, on an open set U. What local surjectivity gives us is that locally, G has a preimage. So, in other words, we can find a cover of U, right, cover by UI, such that G restricted to each UI has a preimage, Fi. Okay, so what is the problem? Well, now, unlike in the injectivity case, we might not be able to glue this Fi together because they might not be compatible. These local preimages might not agree on intersection, so then they cannot glue to a global preimage. Thus, we see that the obstacle here is that local preimages might not glue to global preimages. And thus, we want to define this H1, this cohomology, in such a way that it measures the extent to which local preimages fail to glue to a global preimage. So the image of G in this group should capture the compatibility of the local preimages. Thus, maybe we can think of elements of this group as, say, tuples. Right, on each uij, we take the element fi minus fj. By uij here, I mean ui intersect with uj. And then we define some equivalence relation on this, so that we have exactness here. That means the image of G is trivial, i.e. G lies in the kernel here, if and only if G is in the image of this, i.e. G actually has a global preimage. So what should we quotient out by? When does G comes from a global preimage? Well, at first glance, you might say we should require these preimages to be compatible. Well, that's indeed sufficient. If they are compatible, then indeed they will glue to a global preimage. But is that really necessary? Remember that the preimages here, they are not unique. On each UI, if Fi is a preimage, then if we add another element in the kernel of the map restricted to UI, we get another preimage on UI. So maybe this particular set of preimages do not glue, but that doesn't mean that the G doesn't have a global preimage. Maybe we can choose a different set of preimages on the same UI, right? So the sufficient and necessary condition for G to have a global preimage would be that if there exists element Ki in these kernels, such that when we modify the preimages, local preimages Fi by Ki, we get a compatible set of preimages. So these will glue together to a global preimage. So now we will rewrite this condition as follows. And this gives us a way to define the H1. Maybe we can think of H1 as follows. So its elements are tuples, right? Tuples of section of the kernel on Uij, right? Because this lies in the kernel. Because Fi and Fj maps to the same thing, maps to G, right? In Uij, so they both lie in the kernel of the map restricted to Uij. So the elements of H1 here, we can think of them as tuples. We have element Hij lie inside Kij, okay, and mod out by, so the zero elements are gonna be the ones that come from differences of two elements in the kernel. So this Ki here should be sections on the bigger open set, Ui. But this doesn't seem so well defined because it seems to depend on a choice of a covering, right? So this will motivate the definition of the chain complex associated with this cohomology. And this doesn't seem quite right? You should have some questions, because this definition seems to depend on the choice of a cover, Uij. Here in this case I should say that this Uij is a cover of X. So we'll discuss that in the next video.